Tonight on the Cosmic Atlas, we're drifting gently through the vast cosmic ocean, where ancient starlight whispers secrets across billions of years, and we find ourselves drawn toward one of the universe's most magnificent and powerful stellar giants, a Rayet star. In the quiet space of infinite darkness, punctuated by the soft glow of distant galaxies, we begin a contemplative journey that will carry us through layers of cosmic wonder, each more beautiful and mysterious than the last. Like whispers in the night, the story of Rayet stars begins long ago, when the universe was younger, and the first massive stars were born from the primordial hydrogen and helium that filled the cosmic void. These stellar titans, born with masses 25 to 50 times greater than our gentle sun, burn with an intensity that transforms the very fabric of space around them. Gently we discover that these are not ordinary stars, but cosmic laboratories, where the elements of life itself are forged in nuclear fires that burn at temperatures exceeding to 0000 Kelvin, at their surfaces some reaching the almost incomprehensible heat of 210,000 Kelvin. In the quiet space of our imagination, we can picture these massive stars as they exist in their brief but brilliant lifetimes, lasting only a few million years compared to our sun's leisurely 10 billion year journey. The Rayet phase represents the final chapters in the life of these stellar giants, when they have already lived through their main sequence years and are now in their death throes, casting off their outer layers in spectacular displays of cosmic artistry that create some of the most beautiful nebulae in our galaxy. As our journey continues into this realm of stellar magnificence, we find ourselves approaching our chosen Rayet star from the comfortable safety of deep space, where we can observe and contemplate its majesty without the harsh realities that would actually befall any physical traveler. This is a journey of the mind and spirit, where we can experience the wonder of these cosmic phenomena while wrapped in the peaceful embrace of scientific understanding and imagination. Gently, we discover that Rayet stars are classified into different subtypes, each representing a different stage in their evolution, or a different composition of their outer layers. The WN sequence shows us stars that are rich in nitrogen, while the WC sequence reveals stars abundant in carbon and oxygen. There are also the rare WO stars, which burn so intensely that they represent the very final stages, before these titans either collapse into black holes or explode as supernovae, scattering their enriched material across the cosmos to seed future generations of stars and planets. Like whispers in the night, the stellar winds of Rayet stars carry away enormous amounts of mass each year, sometimes losing the equivalent of our entire Earth's mass every single year. These winds, driven by the intense radiation pressure from the star's core, travel at speeds of thousands of kilometers per second, creating shock waves and spectacular interactions with the surrounding interstellar medium. The result is often the formation of beautiful, expanding bubbles of hot gas and plasma, illuminated by the star's intense ultraviolet radiation and visible across vast distances as some of the most photogenic objects in astronomical imaging. In the quiet space of cosmic perspective, we begin to understand that these stars are not just individual objects of beauty, but crucial players in the chemical evolution of the universe. They are the factories where carbon, oxygen, neon, magnesium, silicon, and many other elements heavier than hydrogen and helium are created through nuclear fusion processes deep within their cores. When these stars eventually end their lives in spectacular supernova explosions, they distribute these elements throughout space, enriching the interstellar medium and providing the raw materials from which rocky planets like Earth and ultimately life itself can form. As our journey continues, we begin our gentle approach toward our chosen Rayet star, a magnificent specimen that we'll call Dream, a star that began its life with about 40 solar masses, and has now through its powerful stellar winds shed nearly half of that mass into the surrounding space. From our vantage point several light years away, our Dream appears as an incredibly bright, blue-white point of light, outshining our sun by a factor of hundreds of thousands. Even at this vast distance, we can observe the telltale signs that mark this as a Rayet star. The characteristic emission lines in its spectrum, the evidence of high-velocity mass loss, and the faint glow of the expanding nebula that surrounds it like a cosmic cocoon. Let's drift into a closer examination of what makes Wolf-Rayet stars so distinctive. In the stellar zoo, unlike main sequence stars like our Sun, which burn hydrogen in their cores and maintain relatively stable surface conditions, Wolf-Rayet stars have evolved beyond this peaceful equilibrium. They have exhausted the hydrogen in their cores and moved on to burning helium, carbon, and heavier elements in a series of increasingly energetic fusion reactions. This advanced nuclear burning releases tremendous amounts of energy, creating radiation pressures so intense that they literally blow away the star's outer layers. At tremendous speeds, the surface of a Wolf-Rayet star presents a unique spectacle in astrophysics. Unlike our Sun, whose surface shows absorption lines where cooler gases absorb specific wavelengths of light, Wolf-Rayet stars show prominent emission lines. These bright spectral features are created in the star's extensive hot atmosphere, where the intense radiation from the stellar core ionizes and excites atoms in the outflowing stellar wind. The most prominent of these lines come from highly ionized carbon, nitrogen, oxygen, and helium, creating a spectral fingerprint that immediately identifies these stars to astronomers. Now we float toward a more detailed understanding of the stellar winds that make Wolf-Rayet stars so remarkable. These winds are not gentle breezes like the solar wind that carries aurora-inducing particles to Earth. Instead, they are torrential gales of plasma and particles, accelerated to velocities of 1,000 to 5,000 kilometers per second by the immense radiation pressure generated in the star's interior. To put this in perspective, these winds travel fast enough to cross the entire diameter of Earth in just a few minutes. Gently, we discover that the mass loss rates of Wolf-Rayet stars are truly staggering by stellar standards. While our Sun loses about 1 Earth mass worth of material every 150 million years through the solar wind, a typical Wolf-Rayet star can lose the equivalent of Earth's entire mass every single year. Over the course of its Wolf-Rayet phase, which lasts perhaps 100,000 to 500,000 years, such a star might shed 10 to 20 solar masses of material, fundamentally altering its structure and evolution. Like whispers in the night, these stellar winds carry with them the products of nuclear fusion from deep within the star's interior. Carbon atoms forged in the helium-burning core, oxygen created through successive fusion reactions, and trace amounts of heavier elements all stream outward at incredible velocities. As this material moves away from the star, it begins to cool, and can sometimes condense into tiny grains of dust, creating some of the first solid matter in the universe from elements that were pure energy just moments before. In the quiet space of our contemplation, we can imagine the complex dance of physics that drives these spectacular stellar winds. Deep within the Wolf-Rayet star's core, nuclear fusion reactions are proceeding at rates millions of times greater than those in our Sun's core. The energy generated by these reactions creates intense radiation fields that propagate outward through the star's interior. When this radiation encounters the partially transparent outer layers of the star, it transfers momentum to the gas through a process called radiation pressure. This radiation pressure acts like an invisible hand, pushing outward on the stellar material with a force that eventually overcomes the star's gravitational pull. Once this critical point is reached, the outer layers of the star begin to accelerate outward, creating the characteristic high-velocity stellar wind. The process is self-reinforcing. As material flows away from the star, it becomes less dense, allowing radiation to penetrate even more effectively and drive even higher mass loss rates. As our journey continues deeper into the realm of Wolf-Rayet phenomena, we encounter one of the most beautiful consequences of these powerful stellar winds: the creation of magnificent nebulae that surround many Wolf-Rayet stars, like cosmic gardens of light and color. These structures, sometimes called Wolf-Rayet bubbles, form when the high-speed stellar wind collides with slower-moving material that was ejected during earlier phases of the star's evolution. The interaction between these different velocity regimes creates shock waves that heat the gas to millions of degrees, causing it to emit X-rays and other high-energy radiation. The visible light we see in photographs of these nebulae comes from the recombination of ions and electrons in the cooling gas behind these shock fronts. creating the characteristic red glow of hydrogen, the blue-green tints of doubly ionized oxygen, and the subtle colors contributed by other elements. Let's drift into an appreciation of some of the most famous Wolf-Rayet nebulae, each one a unique masterpiece of cosmic art. The Crescent Nebula, associated with the Wolf-Rayet star WR136, presents a delicate arc of glowing gas that resembles a cosmic smile, painted across the darkness of space. The nebula's structure reveals the complex interplay between stellar winds of different epochs, creating layers and filaments that tell the story of the star's evolution over hundreds of thousands of years. Similarly, the Ring Nebula in Lyra, though not associated with a Wolf-Rayet star, in its current state shows us what the final stages of stellar evolution can create when a star's powerful stellar winds interact with previously expelled material. The intricate braided structures, the delicate ionization boundaries, and the overall symmetry of such nebulae speak to the fundamental physical processes that govern the behavior of matter and energy in extreme astrophysical environments. Gently, we discover that the study of Wolf-Rayet stars and their associated nebulae has provided crucial insights into stellar evolution, nuclear synthesis, and the chemical enrichment of galaxies. By analyzing the composition of Wolf-Rayet stellar winds, astronomers can directly observe the products of nuclear burning that normally remain hidden deep within stellar cores. The relative abundances of carbon, nitrogen, oxygen, and other elements tell us about the nuclear reactions that have occurred and provide tests of our theoretical understanding of stellar evolution. Now we float toward the consideration of our hypothetical journey into one of these stellar giants. From our current position, still safely distant from WR Dream, we can begin to imagine what it would be like to approach this cosmic furnace. Of course, any realistic journey toward a Wolf-Rayet star would result in our immediate vaporization long before we reached even the outermost edges of the stellar wind. But in the realm of imagination and scientific exploration, we can consider what such a journey might reveal about the nature of matter and energy under extreme conditions. In the quiet space of scientific thought, we must first acknowledge that our hypothetical traveler would need to be made of something far more resilient than ordinary matter. Perhaps we are a consciousness riding on a probe made of exotic matter that can withstand temperatures of millions of degrees and pressures billions of times greater than Earth's atmosphere. Or perhaps we are pure information, able to experience and record the phenomena we encounter without being destroyed by them. As our journey continues inward toward WR Dream, we would first encounter the outer edges of the stellar wind, at distances of perhaps 100 to 1,000 times the radius of the star itself. Here, the wind has already accelerated to significant fractions of its terminal velocity, creating a tenuous but incredibly hot envelope of expanding plasma. The density would still be extraordinarily low by terrestrial standards, much lower than the best vacuum achievable in Earth-based laboratories, but the kinetic energy of the individual particles would be enormous. Like whispers in the night, the first signs of our approach into the stellar wind regime would be subtle but unmistakable. The background temperature of space, normally just a few degrees above absolute zero, would begin to rise as we encounter increasing numbers of high-energy particles streaming outward from the star. Our instruments would detect the characteristic spectral signatures of highly ionized atoms, carbon atoms stripped of most of their electrons, oxygen ions glowing with the energy of their quantum transitions, and helium ions excited to states impossible under normal stellar conditions. The light around us would begin to change as well. The intense ultraviolet and X-ray radiation from WR Dream would ionize any gas or dust in our vicinity, creating a faint aurora-like glow as particles recombined and released photons. The star itself would appear increasingly bright and blue-white, its surface temperature of perhaps 50,000 Kelvin making it shine with a harsh, almost alien light compared to the warm yellow glow of our familiar sun. Gently, we discover that the journey inward through the stellar wind would be a gradual transition rather than a sharp boundary. The density of the wind increases roughly as the inverse square of the distance from the star, meaning that as we have our distance, the number of particles around us quadruples. The temperature, however, might actually decrease as we move inward through certain regions. as the expanding gas cools through adiabatic expansion, only to be reheated by absorption of the star's intense radiation. As we continue our inward drift, we would encounter regions where the stellar wind interacts with clumps of denser material, perhaps remnants from earlier phases of mass loss, when the star was still in its red supergiant phase. These interactions create shock waves and turbulence that heat the gas to millions of degrees, producing the X-ray emission that astronomers observe from many Wolf-Rayet stars. From our perspective within this environment, we might experience these shock fronts as sudden increases in temperature and pressure, accompanied by bursts of high-energy radiation. Now we float toward the remarkable transition region where the stellar wind transitions from being optically thin to optically thick. In the outer regions of the wind, individual photons from the star can travel long distances without being absorbed or scattered. But as we move closer to the star and the density increases, the wind becomes increasingly opaque to the star's radiation. This transition has profound effects on the wind's acceleration and structure. In the optically thick region, the stellar wind becomes a complex, turbulent medium where radiation and matter are strongly coupled. Photons are repeatedly absorbed and re-emitted by atoms and ions in the wind, creating a diffusion process that can significantly alter the wind's temperature and velocity structure. This is the region where much of the wind's acceleration actually takes place, as the trapped radiation field exerts pressure on the outflowing material. Let's drift into a more detailed consideration of what we might observe in this transition region. The intense radiation field would create conditions unlike anything found in normal stellar atmospheres. Line-driven instabilities would cause the wind to become clumpy and variable, with dense knots of material surrounded by regions of lower density. These structures would be constantly evolving, creating a dynamic, ever-changing environment where the laws of radiation hydrodynamics play out on scales, from kilometers to astronomical units. The spectral appearance of the star would also change dramatically. As we penetrate deeper into the wind, the characteristic emission lines that define Wolf-Rayet spectra are formed in this region, where the combination of high temperature, low density, and intense radiation field creates conditions that favor the emission of photons, rather than their absorption. We would be immersed in a glowing medium where atoms are constantly being ionized and recombining, creating a symphony of light across the electromagnetic spectrum. Gently, we discover that the temperature structure in this region is far from uniform. Radiative heating and cooling compete with adiabatic expansion and compression, creating temperature gradients that can span orders of magnitude over relatively short distances. In some regions, the gas might be heated to temperatures of several 100,000 degrees by the absorption of X-rays and extreme ultraviolet photons. In others, rapid expansion and radiative cooling might reduce the temperature to tens of thousands of degrees. As our journey continues ever inward, we approach what might be considered the photosphere of the Wolf-Rayet star, the region from which most of the star's visible light emerges. Unlike the well-defined photosphere of a normal star like our Sun, the surface of a Wolf-Rayet star is a gradual transition zone, where the stellar wind becomes so dense that it becomes opaque to most wavelengths of light. This photospheric region is a dynamic, turbulent environment where convection, radiation pressure, and mass loss all interact in complex ways. The effective temperature we measure for the star is determined by the conditions in this region, but the actual temperature structure can be quite complicated, with hot spots and cool regions coexisting in close proximity. From our vantage point within this medium, we would be surrounded by a blazing inferno of radiation and rapidly moving particles. In the quiet space of our contemplation, we can try to imagine what it would be like to exist within the photosphere of a Wolf-Rayet star. The pressure would be thousands of times greater than Earth's atmospheric pressure at sea level, while the temperature would exceed 50,000 degrees hot enough to ionize virtually any atom and strip electrons from all but the most tightly bound atomic cores. The density, however, would still be much lower than that of ordinary air, creating a paradoxical environment of high temperature and pressure but relatively low mass density. The radiation field in this region would be dominated by ultraviolet and X-ray photons, carrying energies far exceeding anything encountered in normal stellar atmospheres. This radiation would be so intense that it would exert significant pressure on any material in its path, contributing to the outward acceleration of the stellar wind. From a human perspective, this environment would represent one of the most extreme radiation fields in the universe, capable of breaking apart atomic nuclei and creating exotic states of matter. Now we float toward the deeper interior of WR Dream, penetrating through the photosphere into the convective zone that lies beneath. In normal stars, convective zones transport energy from the hot interior to the cooler surface through the physical motion of hot gas upward and cool gas downward. In Wolf-Rayet stars, these convective motions are extraordinarily vigorous, driven by the intense energy generation in the core and modified by the effects of rapid mass loss. The convective zone of a Wolf-Rayet star is a chaotic, turbulent environment where hot bubbles of gas rise from the interior, while cooler material sinks inward in a complex three-dimensional dance. The velocities of these convective motions can reach hundreds of kilometers per second, creating an environment where the boundary between up and down becomes meaningless, as material churns and mixes in all directions. Like whispers in the night, the convective motions carry with them the products of nuclear burning from the star's core, carbon atoms created through helium fusion, oxygen produced by carbon burning, and traces of heavier elements all participate in this convective mixing, gradually working their way outward, toward the surface where they can eventually be expelled in the stellar wind. This mixing process is crucial for understanding the chemical composition we observe in Wolf-Rayet, stellar winds, and the role these stars play in galactic chemical evolution. As we continue our inward journey through the convective zone, we would encounter ever-increasing temperatures and pressures. The temperature might rise from the 50,000 degrees of the photosphere to several 100,000 degrees in the deeper convective layers. The pressure would increase correspondingly, reaching values millions of times greater than Earth's atmospheric pressure. Under these conditions, matter behaves in ways that are difficult to imagine from our terrestrial perspective. Gently, we discover that the structure of matter itself becomes altered under these extreme conditions. At the temperatures prevailing in the deeper convective zone, atoms are completely ionized, with electrons and nuclei existing as separate particles in a plasma state. The high density means that these particles are packed closely together, but the extreme temperature ensures that they move at velocities of hundreds of kilometers per second, creating a dynamic environment where quantum effects and classical physics both play important roles. The radiation field within the convective zone is incredibly intense, dominated by X-rays and gamma rays produced by the thermal motion of the hot plasma. This radiation is so energetic that it can interact directly with atomic nuclei, influencing nuclear reaction rates and creating exotic isotopes that cannot be produced under normal stellar conditions. From our perspective within this environment, we would be bathed in a flood of high-energy photons carrying information about the fundamental physical processes occurring around us. Let's drift into the transition region between the convective zone and the star's nuclear burning core. This boundary represents one of the most important regions in the star's interior, where the energy generated by nuclear fusion begins its journey outward toward the surface. In a Wolf-Rayet star, this transition can be quite complex, as the rapid evolution of the star's interior structure creates conditions that change dramatically over relatively short timescales. The core of WR Dream is where the star's most energetic nuclear reactions take place. Unlike our Sun, which burns hydrogen through the relatively gentle proton-proton chain reaction, Wolf-Rayet stars have moved beyond hydrogen burning to more energetic fusion processes. In the core, helium nuclei fuse together to create carbon through the triple alpha process, while in surrounding shells, carbon nuclei undergo fusion to produce oxygen, neon, and magnesium. As our journey continues into this nuclear furnace, we encounter temperatures that exceed 100 million degrees, conditions so extreme that the very notion of temperature, based as it is on the average kinetic energy of particles, begins to lose its familiar meaning. At these temperatures, particles move at significant fractions of the speed of light, and relativistic effects become important in determining the behavior of matter and energy. Now we float toward the very heart of nuclear fusion processes that power WR Dream. The triple alpha process, which converts 3 helium for nuclei into a single carbon-12 nucleus, requires temperatures of at least 100 million degrees to overcome the electromagnetic repulsion between the positively charged helium nuclei. This process is much more temperature sensitive than hydrogen burning, meaning that small changes in core temperature can lead to dramatic changes in energy generation rates. In the quiet space of nuclear physics, we can appreciate the elegant simplicity of the fusion reactions occurring around us. Each fusion event releases a precise amount of energy, determined by the difference in binding energy between the reactants and products. This energy appears initially as kinetic energy of the reaction products, but is quickly thermalized through collisions with surrounding particles, contributing to the thermal energy that drives the star's structure and evolution. The carbon nuclei produced by helium burning do not remain idle in the stellar core. As the temperature continues to rise due to gravitational contraction and continued energy generation, these carbon nuclei become the fuel for the next stage of nuclear burning. Carbon fusion, which requires temperatures of about 600 million degrees, produces a variety of products including oxygen, neon, sodium, and magnesium, along with additional helium nuclei that can participate in further helium burning reactions. Gently, we discover that the nuclear processes in the core of a Wolf-Rayet star create a complex network of interconnected reactions, where the products of one fusion process become the reactants for another. This nuclear reaction network is responsible for the synthesis of many of the elements between carbon and iron in the periodic table, making Wolf-Rayet stars crucial contributors to the chemical diversity of the universe. The energy generation rate in the core of WR Dream is truly staggering. Each cubic centimeter of the core produces more energy per second than the entire output of a typical nuclear power plant on Earth. This energy must somehow make its way to the star's surface, a vast distance of hundreds of thousands of kilometers before it can be radiated away into space. The mechanisms by which this energy transport occurs help determine the star's structure, evolution, and ultimate fate. Like whispers in the night, energy leaves the nuclear burning core primarily in the form of high-energy photons, gamma rays, produced by nuclear reactions and by the thermal motion of the incredibly hot plasma. These photons begin a long, tortuous journey outward through the star's interior, repeatedly absorbed and re-emitted by atoms and ions in their path. This radiative diffusion process can take thousands of years for energy produced in the core to finally escape from the star's surface. As we contemplate our position deep within the stellar core, we can imagine ourselves surrounded by a sea of gamma-ray photons, each carrying a tiny fraction of the star's total energy output. On their journey toward the surface, the density of these photons is so high that they exert significant pressure on the surrounding matter, contributing to the support of the star against gravitational collapse. This radiation pressure becomes increasingly important in massive stars, eventually becoming the dominant pressure component in the most massive Wolf-Rayet stars. The matter surrounding us in the core exists in a state that has no terrestrial analog. The density is comparable to that of water, but the temperature is millions of times higher than anything achieved in Earth-based laboratories. Under these conditions, the properties of matter are determined by a complex interplay between quantum mechanics, thermodynamics, and relativity. Electrons become partially degenerate, meaning that their behavior is influenced by the Pauli exclusion principle, while nuclei remain in a classical regime but move at velocities that approach relativistic speeds. As our journey continues within the stellar core, we can observe the delicate balance of forces that determines the star's structure. Gravitational force pulls all material inward, while radiation pressure and gas pressure push outward. The balance between these forces determines the density and temperature at each point within the star, creating the conditions necessary for nuclear fusion while preventing catastrophic collapse. Now we float toward an understanding of how the rapid mass loss characteristic of Wolf-Rayet stars affects the structure of the stellar core. As the star's outer layers are blown away by the powerful stellar wind, the core is gradually exposed, leading to changes in the star's overall structure and evolution. The reduction in the overlying mass reduces the gravitational pressure in the core, potentially affecting nuclear burning rates and the star's energy output. This mass loss also has profound implications for the star's ultimate fate. A star that begins its life with 40 solar masses might end its Wolf-Rayet phase, with only 10 to 15 solar masses remaining, fundamentally altering whether it will explode as a supernova collapse directly to a black hole, or perhaps undergo some other exotic end state. The amount of mass lost during the Wolf-Rayet phase is thus a crucial parameter in determining the star's contribution to galactic chemical evolution and the population of stellar remnants. In the quiet space of stellar evolution theory, we can appreciate how Wolf-Rayet stars represent a critical phase in the life cycles of the most massive stars. They serve as a bridge between the main sequence phase, when stars burn hydrogen in their cores, and the final explosive phases that distribute heavy elements throughout the galaxy. Without the mass loss that characterizes Wolf-Rayet stars, many massive stars would evolve quite differently, potentially becoming even more exotic objects like parent stability supernovae or collapsing directly into black holes without enriching the interstellar medium. Gently, we discover that our journey to the heart of our dream has revealed the intimate connection between nuclear physics, stellar structure, and galactic evolution. The carbon and oxygen atoms being forged in nuclear reactions around us will eventually be expelled in the stellar wind, contributing to the material from which future generations of stars and planets will form. In a very real sense, we are witnessing the birth of the elements that make rocky planets and life itself possible. The nuclear processes occurring in the stellar core also provide crucial insights into fundamental physics under extreme conditions. The reaction rates, energy generation mechanisms, and equilibrium abundances of various nuclear species all depend on our understanding of quantum mechanics, thermodynamics, and nuclear physics. Observations of Wolf-Rayet stars and their chemical compositions provide important tests of these physical theories under conditions that cannot be replicated in terrestrial laboratories. As we contemplate the incredible energies and temperatures surrounding us in the stellar core, we can also appreciate the remarkable stability of the nuclear fusion processes that power our dream. Despite the extreme conditions, the fusion reactions proceed in an orderly, predictable manner, governed by well-understood physical laws. This stability allows the star to maintain its structure and energy output for hundreds of thousands of years during its Wolf-Rayet phase, providing time for the complex interplay between nuclear burning, mass loss, and stellar evolution to play out. Let's drift into a consideration of the various nuclear burning shells that surround the core of our dream. In addition to the central helium burning core, there are likely several concentric shells where different nuclear reactions are taking place. A hydrogen burning shell might persist in the outer regions, where hydrogen has not yet been completely depleted, while various helium-burning shells contribute to the overall energy output of the star. These multiple burning shells create a complex, layered structure within the star's interior, with each shell operating under slightly different conditions of temperature, density, and composition. The interactions between these shells can lead to instabilities and oscillations that affect the star's surface properties and mass loss rate. Some theoretical models suggest that these instabilities might be responsible for the clumpy, variable nature of Wolf-Rayet stellar winds. The composition of material in the various burning shells provides a fossil record of the star's previous evolution. Elements produced during earlier burning phases become incorporated into the stellar wind, as convective mixing and mass loss expose progressively deeper layers of the star. By analyzing the composition of Wolf-Rayet stellar winds, astronomers can infer the nuclear burning history of these stars and test theoretical models of massive star evolution. Now we float toward the realization that our hypothetical journey into our dream has taken us through a complete cross-section of one of the universe's most extreme stellar environments, from the tenuous outer reaches of the stellar wind to the nuclear furnace of the core. We have experienced conditions that span more than 10 orders of magnitude in density and pressure, and temperatures ranging from thousands to hundreds of millions of degrees. In the quiet space of scientific reflection, we can appreciate how this journey has illuminated the fundamental connections between microscopic nuclear physics and the macroscopic evolution of stars and galaxies. The nuclear reactions occurring in the stellar core determine the star's energy output and lifetime, while the resulting radiation field drives the powerful stellar winds that enrich the interstellar medium with heavy elements. This intimate connection between the very small and the very large is one of the most beautiful aspects of astrophysics. Like whispers in the night, the story of Wolf-Rayet stars reminds us of our own cosmic heritage, the carbon in our bodies, the oxygen we breathe, and many of the other elements essential for life were forged in the nuclear furnaces of massive stars like WR Dream. When these stars eventually explode as supernovae or shed their outer layers as planetary nebulae, they distribute these life-enabling elements throughout the galaxy, seeding the formation of new stars, planets, and ultimately life itself. Gently, we discover that Wolf-Rayet stars also play crucial roles in shaping the structure and evolution of galaxies. Their powerful stellar winds and eventual supernova explosions inject enormous amounts of energy into the interstellar medium, driving turbulence, triggering star formation in some regions while suppressing it in others. The hot bubbles and cavities created by Wolf-Rayet winds can persist for millions of years, influencing the distribution and properties of gas throughout the galaxy. The intense ultraviolet radiation from Wolf-Rayet stars also has profound effects on their surroundings. This radiation can ionize hydrogen gas out to distances of hundreds of light years, creating vast H2 regions that shine with the characteristic red glow of hydrogen recombination radiation. These ionized regions affect the thermal structure of the interstellar medium and influence the formation and evolution of molecular clouds when new stars are born. As our journey through WR Dream comes to its conclusion, we find ourselves transformed by the experience, having witnessed firsthand the incredible beauty and complexity of stellar interiors. We have seen how nuclear physics, thermodynamics, radiation transport, and fluid dynamics all work together to create and maintain one of the universe's most spectacular phenomena. The journey has revealed the intimate connections between stars and their environments, between nuclear reactions and galactic evolution, and between the processes that occurred billions of years ago and the composition of the Earth on which we live. As our journey continues toward its peaceful conclusion, we can reflect on the broader implications of what we have experienced. During our voyage through WR Dream, Wolf-Rayet stars represent a crucial phase in cosmic evolution, serving as both the death throes of massive stars and the birth announcements of the heavy elements that make complex chemistry and life possible. They are simultaneously among the universe's most destructive forces, capable of sterilizing entire regions of space with their intense radiation and stellar winds, and among its most creative forces, synthesizing the building blocks of planets and living beings. The study of Wolf-Rayet stars has also provided crucial insights into the limits of stellar physics and the behavior of matter under extreme conditions. These stars operate near the maximum possible luminosity for objects of their mass, a limit set by the balance between radiation pressure and gravitational attraction, known as the Eddington limit. Understanding how Wolf-Rayet stars can maintain their structure while producing luminosities that approach or even exceed this theoretical maximum has advanced our knowledge of stellar atmospheres, radiation transport, and stellar stability. Let us drift into a contemplation of the observational techniques that have allowed astronomers to study Wolf-Rayet stars and unlock their secrets. The characteristic emission line spectra that first identified these unusual stars continue to provide detailed information about their surface compositions, mass loss rates, and evolutionary status. Modern techniques such as interferometry, which combines light from multiple telescopes to achieve extremely high angular resolution, have allowed astronomers to directly image the immediate environments of Wolf-Rayet stars and study the structure of their stellar winds and surrounding nebulae. Space-based observations have been particularly crucial for advancing our understanding of Wolf-Rayet stars. The intense ultraviolet and X-ray radiation from these stars is largely absorbed by Earth's atmosphere, making ground-based observations incomplete. Satellites such as the Hubble Space Telescope, the Chandra X-ray Observatory, and the recently launched James Webb Space Telescope have provided unprecedented views of Wolf-Rayet stars across the electromagnetic spectrum, revealing details of their stellar wind's chemical compositions and interactions with their environments. Gently, we discover that the population of known Wolf-Rayet stars in our galaxy is actually quite small, numbering only a few hundred confirmed objects. This rarity reflects both the short lifetimes of these stars and the restrictive conditions required for their formation and evolution. Only stars born with masses greater than about 25 times that of our Sun will evolve through a Wolf-Rayet phase, and the duration of this phase is typically only a few 100,000 years, an eye blink compared to the billions of years that lower-mass stars spend on the main sequence. The distribution of Wolf-Rayet stars within our galaxy also tells us important things about stellar evolution and galactic structure. These stars are preferentially found in regions of active star formation, particularly in the spiral arms where massive molecular clouds provide the raw material for creating very high-mass stars. The absence of Wolf-Rayet stars in the galactic halo and in globular clusters reflects the low metallicity of these ancient stellar populations, confirming theoretical predictions that Wolf-Rayet evolution depends on the presence of heavy elements to drive stellar winds. Now we float toward a consideration of the role that Wolf-Rayet stars might play in some of the universe's most energetic phenomena. Some gamma-ray bursts, the most luminous explosions known in the universe, are thought to result from the collapse of rapidly rotating Wolf-Rayet stars into black holes. The extreme angular momentum and magnetic fields present in these stars might allow them to launch relativistic jets of particles and radiation that we observe as gamma-ray bursts when they happen to point in our direction. Wolf-Rayet stars are also prime candidates for producing Type Ib and Type Ic supernovae, which lack the hydrogen lines characteristic of more common Type II supernovae. The absence of hydrogen in these explosions is naturally explained. If the progenitor star has lost its hydrogen-rich outer layers during a Wolf-Rayet phase, leaving behind a helium-rich or oxygen-rich core that eventually undergoes core collapse and explosion, in the quiet space of cosmic perspective, we can appreciate how Wolf-Rayet stars serve as natural laboratories for testing our understanding of extreme physics. The conditions present in these stars temperatures of hundreds of millions of degrees densities, approaching those found in white dwarf stars, magnetic fields that may exceed those of neutron stars, and radiation fields intense enough to drive matter to speeds of thousands of kilometers per second, cannot be reproduced in any terrestrial laboratory. The theoretical modeling of Wolf-Rayet stars requires sophisticated computer simulations that incorporate nuclear physics, radiation transport, magnetohydrodynamics, and stellar structure theory. These models must account for the complex interactions between nuclear burning, convection, mass loss, and magnetic fields, or operating under conditions where the assumptions used in modeling normal stars may no longer be valid. The success of these models in reproducing the observed properties of Wolf-Rayet stars provides confidence in our understanding of the fundamental physics involved. Like whispers in the night, ongoing research continues to refine our understanding of Wolf-Rayet stars and their role in cosmic evolution. New observational techniques, such as astroseismology applied to Wolf-Rayet stars, promise to provide insights into their internal structure and dynamics. Improved theoretical models, incorporating three-dimensional fluid dynamics and more sophisticated treatments of radiation, transport, and magnetic fields, are revealing new aspects of Wolf-Rayet evolution and mass loss. The discovery of Wolf-Rayet stars in other galaxies has also expanded our perspective on these objects and their cosmic significance. Observations of Wolf-Rayet populations in nearby galaxies with different metallicities and star formation histories have provided tests of stellar evolution theory and insights into how the properties of Wolf-Rayet stars depend on their environments. Some galaxies show surprisingly large numbers of Wolf-Rayet stars, suggesting that environmental factors such as galaxy interactions or active galactic nuclei might influence massive star evolution in ways we don't yet fully understand. As our contemplative journey through the realm of Wolf-Rayet stars draws toward its close, we can reflect on the profound beauty and complexity we have encountered. These stellar giants, burning with the fury of nuclear fire and shedding their substance into the cosmic void, represent some of nature's most spectacular displays of matter and energy in action. They remind us that the universe is a dynamic, evolving system where destruction and creation are intimately linked, where the death of stars provides the materials for new generations of cosmic objects. Gently, we discover that our exploration of Wolf-Rayet stars has also been a journey into our own origins, the elements that make up our bodies, our planet, and indeed all of the complex chemistry that makes life possible, were forged in the nuclear furnaces of massive stars like the one we have visited. When we look up at the night sky and see the faint glow of a distant Wolf-Rayet star, we are seeing light from a cosmic forge that is manufacturing the building blocks of future worlds and future life. The story of Wolf-Rayet stars is ultimately the story of cosmic evolution itself, how simple hydrogen and helium left over from the Big Bang have been processed through successive generations of stars to create the rich chemical diversity we see in the universe today. These stars serve as crucial links in the chain of cosmic evolution that connects the primordial universe to the complex, life-bearing cosmos we inhabit today. Now we float toward our final reflections on this remarkable journey. Through one of the universe's most extreme stellar environments, our hypothetical voyage into WR Dream has taken us from the tenuous outer reaches of the stellar wind through the complex atmospheric layers where emission lines are formed, into the turbulent convective zones, and finally into the nuclear furnace of the stellar core where the elements of life are born. Throughout this journey, we have been guided by the principles of physics that govern the behavior of matter and energy under extreme conditions. We have seen how gravity, radiation pressure, nuclear forces, and thermodynamics all work together to create and maintain these stellar giants. We have witnessed the delicate balance between forces that allows Wolf-Rayet stars to exist as stable, energy-producing systems while simultaneously driving the powerful mass loss that will ultimately determine their fate. In the quiet space of our final contemplation, we can appreciate how our journey has revealed the fundamental interconnectedness of all things in the universe. The nuclear reactions occurring in the cores of Wolf-Rayet stars are governed by the same quantum mechanical principles that determine the properties of atoms in our bodies. The radiation transport processes that carry energy from the stellar core to the surface operate according to the same physical laws that govern the flow of energy from our sun to Earth, enabling photosynthesis and ultimately all life on our planet. Like whispers in the night, the legacy of Wolf-Rayet stars extends far beyond their brief but spectacular lifetimes. The heavy elements they produce and distribute through their stellar winds, and eventual supernova explosions become incorporated into future generations of stars and planetary systems. Some of the carbon atoms forged in the core of a Wolf-Rayet star billions of years ago might now be part of the DNA in our cells, carrying the genetic information that makes us who we are. The cosmic perspective provided by our study of Wolf-Rayet stars also reminds us of our place in the vast sweep of cosmic time and space. These stars live their entire lives from birth to death in a time span that is shorter than the age of complex life on Earth. Yet in that brief cosmic moment, they accomplish the remarkable feat of converting the primordial hydrogen and helium of the early universe into the complex atoms that make chemistry, geology, and biology possible. As we prepare to conclude our peaceful journey through the realm of Wolf-Rayet stars, we can carry with us a deeper appreciation for the beauty and complexity of the universe we inhabit. These stellar giants burning with temperatures that exceed the core of our sun by factors of thousands remind us that the cosmos is a place of incredible extremes, where matter and energy can exist in states that challenge our imagination and expand our understanding of what is possible. The gentle process of scientific discovery that has revealed the secrets of Wolf-Rayet stars, from their first identification through spectroscopy to our current sophisticated understanding of their structure and evolution, exemplifies humanity's ongoing quest to understand our cosmic environment. Each new observation, each refined theoretical model, each successful prediction adds another piece to the grand puzzle of cosmic evolution and our place within it. Gently, we discover that the study of Wolf-Rayet stars continues to evolve as new observational capability and theoretical insights become available. Future space telescopes, with even greater sensitivity to ultraviolet and X-ray radiation, will provide more detailed views of Wolf-Rayet stellar winds and their interactions with the interstellar medium. Advanced computer simulations running on ever more powerful computers will incorporate increasingly sophisticated physics to model the complex three-dimensional structure of these stars and their evolution over time. The field of time-domain astronomy, which studies how astronomical objects change over time, is also opening new windows into Wolf-Rayet star physics. Some Wolf-Rayet stars show periodic or irregular variations in their brightness and spectral properties, potentially revealing information about their internal structure, rotation, magnetic fields, or interactions with companion stars. Long-term monitoring programs are beginning to reveal the statistics of these variations and their implications for our understanding of Wolf-Rayet evolution. As our journey continues toward its peaceful conclusion, we can also contemplate the philosophical implications of our exploration. The fact that we, as conscious beings made of atoms forged in stellar cores, can study and understand the very processes that created us, represents one of the most remarkable achievements of the human intellect. We are literally star stuff contemplating stars, cosmic matter that has become organized in such a way as to be capable of understanding its own origins and evolution. This self-reflective aspect of astronomy and astrophysics gives the study of objects like Wolf-Rayet stars a profound meaning that goes beyond mere scientific curiosity. By understanding these stars, we understand something fundamental about ourselves and our relationship to the cosmos. We learn that we are not separate from the universe but intimately connected to it, through the very atoms that make up our bodies and the physical laws that govern our existence. Let us drift into our final moments of contemplation as we prepare to leave the realm of our dream and return to the peaceful darkness of interstellar space. Our journey has taken us through extremes of temperature, pressure, and energy that represent some of the most intense conditions in the known universe. We have witnessed nuclear fusion in action, seen how radiation pressure can overcome gravitational attraction, and observed the delicate balance of forces that allows these stellar giants to exist. Throughout our exploration, we have maintained a sense of wonder and reverence for the natural processes we have observed. The incredible complexity and beauty of Wolf-Rayet stars, from their spectacular stellar winds to their crucial role in galactic chemical evolution, remind us that the universe is a place of profound mystery and endless fascination. Each new discovery opens up new questions, each answered question reveals new depths of complexity, and each moment of understanding brings with it a deeper appreciation for the magnificent cosmos we inhabit. Now we float toward our gentle departure from our dream, carrying with us the memories and insights gained during our remarkable journey. As we move outward through the stellar wind, past the emission line formation regions, and back into the relative peace of interstellar space, we can reflect on how our understanding has been enriched by this experience. We have seen firsthand how the universe creates the elements essential for life, how massive stars shape their galactic environments, and how the laws of physics operate under the most extreme conditions nature can provide. In the quiet space of our cosmic perspective, we can appreciate how Wolf-Rayet stars serve as beacons of scientific understanding, illuminating fundamental processes that operate throughout the universe. The insights gained from studying these stellar giants have applications far beyond stellar astrophysics, informing our understanding of nuclear physics, fluid dynamics, radiation transport, and the behavior of matter under extreme conditions. The journey has also reminded us of the importance of curiosity-driven research and the value of studying phenomena that might seem distant from our everyday experience. While Wolf-Rayet stars might appear to have little direct relevance to life on Earth, our exploration has revealed the profound connections between these stellar giants and our own existence. The elements they create, the energy they release, and the environments they shape all play crucial roles in the cosmic ecosystem that makes planets like Earth and life like ours possible. Gently, we discover that our contemplative journey through the realm of Wolf-Rayet stars has been both an exploration of external cosmic phenomena, and an internal journey of discovery and wonder. By opening our minds to the incredible beauty and complexity of these stellar giants, we have expanded our appreciation for the natural world and our place within it. We have been reminded that we live in a universe of astounding richness and diversity, where even the most extreme and seemingly alien environments follow the same fundamental physical laws that govern our everyday experience. Like whispers in the night, the knowledge we have gained during our journey will continue to resonate long after we have returned to the familiar surroundings of our terrestrial perspective. The images of stellar winds carrying heavy elements into space of nuclear fusion reactions, creating the building blocks of future worlds, and of the delicate balance between creation and destruction that characterizes these stellar giants, will remain with us as reminders of the incredible processes that have shaped our universe and continue to shape its future evolution. As we complete our peaceful exploration of Rayet stars and prepare for the restorative embrace of sleep, we can carry with us a deeper understanding of our cosmic heritage and a renewed sense of wonder at the natural world. The journey through WR Dream has revealed that even in the most extreme environments the universe can create, there is beauty, order, and meaning to be found. The scientific principles that govern these stellar giants are the same ones that govern the gentler processes that sustain life on Earth, reminding us of the fundamental unity that underlies the apparent diversity of cosmic phenomena. The contemplative approach we have taken to exploring these stellar giants has allowed us to transform what might otherwise be an overwhelming or frightening subject into a source of peace and wonder. By focusing on the beauty of the physical processes involved, the elegant interconnections between different scales of cosmic phenomena, and the profound implications for our understanding of the universe and our place within it, we have found that even the most extreme astrophysical environments can become sources of tranquility and inspiration. Now we float toward the end of our cosmic journey, surrounded once again by the gentle darkness of space, punctuated by the soft light of distant stars and galaxies. Our exploration of WR Dream has enriched our understanding of stellar evolution, nuclear physics, and the chemical evolution of the universe. More importantly, it has provided us with a deeper appreciation for the remarkable cosmos we inhabit and the incredible processes that have made our existence possible. In these final moments of our journey, we can reflect on how the study of Rayet stars embodies some of the finest aspects of human scientific endeavor: the patient observation, careful analysis, creative theoretical modeling, and collaborative effort that have advanced our understanding of these stellar giants, represent humanity at its best, curious, persistent, and driven by a desire to understand the natural world for its own sake. The peaceful completion of our exploration reminds us that learning and wonder need not be sources of stress or anxiety, but can instead be sources of joy, tranquility, and inspiration. By approaching even the most complex and extreme cosmic phenomena with curiosity, patience, and respect, we can find in them not just scientific knowledge, but also beauty, meaning, and a sense of connection to the larger universe of which we are a part. As our journey through the realm of Rayet stars comes to its gentle conclusion, we are left not with a sense of ending, but with a feeling of new beginning. The knowledge and insights we have gained open up new avenues for exploration and discovery, new questions to contemplate, and new wonders to investigate. The universe revealed through our study of these stellar giants is richer, more beautiful, and more fascinating than we might have imagined at the beginning of our journey. In the quiet space of our final reflection, we can appreciate how our exploration has demonstrated that the pursuit of scientific understanding can be a deeply spiritual and transformative experience. By seeking to understand the natural processes that govern Rayet stars, we have gained insights, not just into stellar physics, but into the nature of existence itself, the origins of the elements that make us who we are, and the cosmic processes that will continue to shape the universe long after our brief moment in cosmic history has passed. The gentle conclusion of our journey through WR Dream leaves us with a sense of gratitude for the opportunity to explore and understand. Gratitude for the scientists and astronomers whose work has made such understanding possible, and gratitude for living in a universe rich enough and beautiful enough to reward our curiosity with insights that inspire wonder and promote peace. Good night from the Cosmic Atlas.